here the direction was, so if for instance I had no change in the utility, I must keep the function constant as well. Right? For generalized ordinal potential, no change here. The utility can grow or drop or stay the same, no restrictions. Okay. And how can we get that? The easiest way is to get a cycle, for instance, so that ordinal function does not exist, and the generalized ordinal potential does exist. You can keep just one change. Okay. Now, ordinal potential function has to stay the same. Okay, well, it has to stay the same, stay the same, stay the same, grow. Impossible. Okay, there is a cycle. So this number is strictly larger than itself. Right? So there is no ordinal potential function here, and it's not hard to put a generalized ordinal potential function here. Let it be 1. Let it be, so it has to, no, it doesn't matter what happens here. Like here it has to be lower than that. That's 8. Okay? Where we have an equality, here we can put anything at all. So this is the only constraint that we have for the generalized ordinal potential function. Clear? Everyone? And please do explain what you do. You don't have to write a lot, but give some reasoning so that it's easier for us to actually give you points for what you've done. Because if there is a mistake, and I don't see where this mistake comes from, I can give you 0. But if I see that actually you reasoned in the right way, but then somehow it failed, you still can get partial marks. So do explain yourself. Don't write long letters, but explain your way of thinking. And again, if you have to prove something, you need to prove that. If you need to disprove something, then you can give a counterexample, but do not prove things with examples. People tend to do that. All right. This one, I think, was... Where's the picture? This question was more or less okay. You had to take one of the games and compute the price of anarchy and stability, both in pure and mixed strategies. Okay, so you take any game, you find it's pure. Well, why I asked you to take any of the games from the previous question, because in the previous question, if you gave correct examples, then all of them have pure strategy Nash equilibrium, because all of them have generalized ordinal potential. Okay, so that's why I ask you to take a game from this question. So there we know that there does exist at least one pure strategy Nash equilibrium. If there is a unique one, then you will have that the price of anarchy and the price of stability will be the same. If there are more than one and they give different social welfare, then the price of anarchy and the price of stability can be different. To calculate those With mixed strategies, you would have to find if there is a mixed equilibrium, strictly mixed equilibrium, in addition to the Nash equilibria that the game does have, and if that gives you different expected social welfare, then the price of anarchy and stability may change as well. How may they change? Would they get better or worse? So, well, think just of the space of strategies. Well, that's a simplex. And the pure strategies are extreme points of the simplex. And mixed strategies, everything inside. So now you have more strategies. Right? So the social welfare. So those that you had before are still there. Right? So you only can expand the set of values that you can achieve. So for the price of anarchy, you may go worse. For the price of stability, you may get better. This one was pretty fine, so it was quite easy to see that the only equilibrium here is for half of the agents to take the upper road, for half of the agents to take the lower road, and when the new one from C to D for zero cost was available, then again, the unique Nash equilibrium was to take the route from A, B, C, D. And when the cost, this cost, dropped to 5, then all of a sudden those routes, upper and lower routes again, have become much cheaper than the long one. So all the agents would drop this free road. And if you delete it after that, that does not change anything. They still would stay with the same equilibrium. I think most of you have done that. Any questions on the first one? Okay. Let's move to this. There were two typical mistakes here. One, I find it hard to explain to myself. So one mistake that a few people have made is saying that if the core is non-empty, then the Shapley value must be in the core. This is not true for all cooperative games, so you cannot use this claim. For some games, we have shown for anonymous games, that was so, but it's not true for all the games, so don't do that. Okay, you have to show directly that there is no solution to the core constraints here. Second mistake was of the similar flavor, but if the core is non-empty, then the proportion, then the 1/4, 1/4, 1/4, 1/4 must be in the core. I don't know why. Okay, this is just a guess that. So that is not correct. What you have to do here is, well, look at what constraints have any vector in the core satisfy and find a contradiction. That's it. So we know that x1 plus x2 plus x3 plus x4 have to be equal to 1. And now we have x1 plus x2 greater or equal 3/4. Same for x1 and x3. Same for x1 and x4. And x2, x3, x4, all of them non-negative. Okay, so any element in the core have to satisfy this system. Now let me call them 1, 2, 3, 4, 5, 6. Now from 1 and 5, there are different ways to find a contradiction. I'll just take one that I find easier. Some people, what they did, they summed up these 3 equations, found something. I did differently, but there are a few ways. What you have to do is to find a contradiction in the system so that no vector can satisfy the system. This is to show that the core is empty. Everyone answered the question correctly. The reason they gave was not quite correct for everyone. Okay, so from here we know that the sum wall is 1, and from here we know that these 3 give at least 3/4. That means that what is left for this guy is at most 1/4. Right. Let me call this 7. Now from 7 and 2, 3, 4, I know that x2 and also x3 and also x4, each one of them is what? Greater than half. But the sum of all 4 is 1. Okay, so greater than 1/2, greater than 1/2, greater than 1/2. This guy is non-negative. Contradiction. So this one plus what? 6. Contradiction to 1. Done. Okay, so no vector can satisfy that. So the core indeed is empty. So no proving this by examples, please. Okay. Not start with, let's say we take x equal this or that and show it does not satisfy that. That just showing that that particular vector is not in the core still does not mean that it's empty. Here, well, the first part, I think everyone has done well. So we have to show that the sum of payments for every collision is at least as the value of that collision minus 2. One thing, a little point, that for the grand collision, you actually have to show that the sum of payment equals exactly the value of that collision for the payment vector to be a valid payment vector in imputation. Okay, this is one of the constraints. So for the grand collision, the sum of the payments has to be exactly the value of that collision, and it does hold here. 2 plus 3 plus 4 is 9. Okay. For the others, we have seen that the excess was exactly 2. Now we have to show that this is the best possible, that is, the 2 core is the least core. In other words, for any epsilon core where epsilon is less than 2, epsilon core is empty. Okay, so it's not to show that, what again some people have done, that the same pair of vectors that we had in A is not in the core for epsilon less than 2. That is pretty obvious indeed. That no other vector can be in the core for epsilon less than 2. Okay, so what we do the same as here. Okay, so we write down the constraints for the core. So now we have 3 agents, right? x1 plus x2 plus x3 is 9. And x1 plus x2 is greater or equal 7 minus epsilon. x1 plus x3 is greater or equal 8 minus epsilon. And x2 plus x3 is greater or equal than 9 minus. And now, for this system to have a solution, we will show that epsilon has to be greater or equal than 2. We can sum up these three guys. We will have y's x1 plus y's x2 plus y's x3 greater or equal 15 plus 9, 24 minus 3 epsilon. I can now divide by 2. I get x1 plus x2 plus x3 greater or equal 12 minus 3 divided by 2 epsilon. Now, so this was what? 2 plus 3 plus 4. Now from 1, we know that this equals 9. Right? So now I can forget about this part. And this is the inequality that I have. So I got this greater or equal than that. So epsilon greater or equal than 2. That's it. Again, this is not the only way to find a contradiction. It can be done differently, but it has to be done for, once again, any x. That question was quite easy for everyone, I would say. You found almost all correctly the characteristic function of the game. There was 5, 7, 12 for singletons. Then there was 7, 12, 12 for pairs, and 25 for the Grant coalition. Then to verify that the game is monotone for every coalition, you have to look at all its subsets and to show that their value is lower than the value of the superset, and indeed it does hold for all the coalitions. C, to verify that the game is superlative. It is not. The counterexample is the value of A is 5, the value of B is 7, but the value of the pair is also 7. So the sum of the values of the singletons is greater than the value of the superset, so the game is not relative. Compute the Shapley value. Again, almost everyone have done right. Some people got a little bit confused in computation. The answer was 6, 7, 12. And you had to check if it is in the core of the game or not. The answer is yes, but please do show that. Okay, so for every collision, show that, well, indeed, 6 plus 7 is greater or equal than 7. So this is x1, xa plus xb, well, not x, we sharp the value. And this is the value of a, b. Okay. If you have many coalitions, at least start and say that the same way we check every coalition. And if you haven't made a mistake, that's fine. But don't just give me the answer without any showing how you've done it, because this is what we want to see. So that's this. the last one, there was some small mistake that some people made in the last question. So you all found out that player 1 on his own can complete task 1, 2 and 3 on their own can't do anything. Then S1 and players 1 and 3 can complete T3 and T1 together, 2 tasks. 1 and 4, 1 and 2, T1 and T4, 2 and 3, only T3. Sorry, that's only T2. Okay, and all of them can complete all the tasks. So we had 2 coalitions with value 1, 2 coalitions with value 2, grand coalition with value 5, and singletons 2 and 3 have value 0, as well as the empty coalition. So that was all fine. Computing the nucleolus. Everyone started right. So you found the excesses correctly. You started. Almost everyone started with vector 3, 1, 1. Fine, you can start with any. Okay, if we start with 3, 1, 1, let's do fractions. So we have 1, 2, 3, 1, 2, 1, 3, 2, 3. Okay. We exclude the empty set and the grand coalition because there the excess is always 0. So it's just not interesting. The value of that coalition was 1, so it's 1 minus x1 minus x2 minus x3. 1 and 2 together, 2 minus x1 minus x2. 1 and 3 together, 2 minus x1 minus x2, and 2 and 3 is 1 minus x2. Right. So if we start indeed with the vector 3, 1, 1, then the excess is 1 minus 3 minus 2. Minus 1 minus 1, 2 minus 4 minus 2, 2 minus 4 minus 2, and 1 minus 2 minus 1. So now we want to change the pair of vectors so that we we reduce the maximal excess. Okay, what's the maximal excess here? There are 3 coalitions with maximal excess. Minus 1. Right? It's 2, 3, or the pair 2 and 3. So we can now take some payoff from player 1 and give it to players 2 and 3, so that we take those things up. Now we can do it gradually. Okay, for instance, as some people have done. So let's look at this coalition, singleton 1 and the pair 2 and 3. Let's, for instance, say the excesses, if I move something from there to the pair, they will meet at 1.5. Right? So I will take I will take some pair from the pair from player 1, so that I get minus 3 over 2 here, minus 3 over 2 here. So this guy has to give away half, right? So he's with 5 over 2. We can give all this half, say, to player 2, for instance. Okay. So it's 1 now we recompute those excesses. Okay, I will not do for all of them, but pay attention that since we didn't give any money to this guy, his excess has not changed. Okay, so what some people have done, they stopped here because they said that these coalitions cannot, so that's where they meet. But we had 3 coalitions with maximal excess, and this guy still has a greater excess than those. Okay, so we cannot fix the payoff to agent 1 yet. We still can take something from him and move to agent 3, and then maybe redistribute the money somehow between agent 2 and 3 as well. Okay, and also note that these 2 singletons are the same agents that here. So after that redistribution, you would get 7 thoughts, 4 thoughts, 4 thoughts, and for that vector, the excesses would be, if I remember correctly, minus 4 thoughts for all these singleton sets, and minus 5 thoughts for the pairs. Now, the maximal excesses are for singletons now, right? So this is not maximal excess, we don't care. We look at the maximal excesses, and indeed now, if I increase the payoff to any of them, I damage the excess of the other. So at this point, indeed, we can't do anything else. Yeah.
Would you be allowed to say that since 2 and 3 are symmetrical, x2 should equal x3?
Well, x2 and x3 are symmetrical here, indeed.
And in the other direction.
But you have to be very careful in checking that they are symmetrical. If they're indeed as here, yes, they would need to have the same excess. But I kind of understand why that mistake happened. Is because in the example that we had in class, there was only one collision. Like when we started, there was only one collision with maximal excess. We fixed that excess, and then indeed we could fix the payoff for player 1 and move forward, right? Here you have to check who is still your maximal excess. So either you redistribute that directly right away for both players 2 and 3, or you can do it gradually, but just don't stop before it's time to stop. That's it here. Yeah, I'm out of time. So on Thursday, if you're ready to bring your homeworks in the morning to the class, I'll come and collect your homeworks in the class. And then I can check them on the same day, and you will be able to collect them on Friday. So that's your incentive to do that. And also, if I have 18 works here in class, then I can talk about the solution right away. If I do not have 18 works, that it means that someone still has not submitted that, so I can't say that. But I think the last one was pretty easy, so I would not expect many questions there. And if you have any questions on the material overall, Thursday is the day to ask them. You're welcome to send us emails as well, but if I have all 20 emails in the last day before the exam, you know, and also I will be on the road. So on 17th, I'm flying, so do not expect any answer on that day. Ask me before.